So this concept is heavily asked in interviews because it seems like runnable is a functional interface, meaning it has only one abstract method. We can replace it with a hello everyone. In today's video, we'll be solving some short but tricky multi-threading problems. The kind of problems you might face in interviews, especially when the interviewer tries to test your understanding of the small details. So while solving these, you will automatically revise and reinforce concepts that we have learned earlier. And also you will learn some new concepts like how can lambda expressions be used to create a thread, then monitor objects on synchronized, and probably some of the memory management techniques. Okay, so watch this video till the end and let's dive into our first problem. So this is our first problem named interleaving threads predict the output. Okay, so here we have a class named shared in which we have a print method. This is our main class where we have created an instance of the shared class and created two threads and have started it. And we have passed in this share.print method in both of the threads. First, let's talk about something new that appeared in this code. This part right here, which we haven't discussed in our previous videos yet. So what is this? So you must be knowing that this is a lambda expression. So it's a short and clean way to pass behavior as a code. Here's the interesting part. So let's move into our IDE and see this. So ignore all these for now and focus on what I am writing here. So if I write thread equals to new thread, right? If I see in the suggestion what this particular constructor requires, it requires an instance of runnable type, right? Runnable target, here also runnable target. But what we are actually doing here is we are passing a lambda method. This is completely fine for the compiler. Now what happens behind the scene when we write this lambda method here? So let's see. So in our runnable interface, we can see that our runnable interface is a functional interface, and since this is a functional interface, it can have only one abstract method, and that abstract method is run method itself. Okay, now what happens at compile time? When I write this and try to run it, the compiler recognizes that runnable is a functional interface and also that it has only one abstract method, run method, which needs to be implemented. So whatever is implemented inside the lambda will be associated with that run method itself, right? As there is no other method to associate this with. So whatever we write inside the lambda must be implementation of run method itself. Okay. After that, it verifies that your lambda matches the signature of run. So if I see here, run method does not take any parameters and it returns nothing. Here also our lambda method does not take any parameters and returns nothing. So this concludes that it is the rightful implementation of run method, right? So this is what happens at compile time, and at runtime this lambda function is implicitly behind the scenes converted into the implementation of runnable. Okay, so since runnable is a functional interface, meaning it has only one abstract method, we can replace it with a lambda. Okay, now let's get back to the problem and let's understand what's going on there. Okay, so here we have a class named shared, and in our main class what we have done is we have created instance of this shared class and created two threads and have started that. Okay. And what is the implementation of run method? Inside the run method, we are doing share.print and share.print. We are calling this particular function. Now, since we have used synchronized here, so either T1 will enter or T2 will enter at any point of time, right? Both cannot enter. Now the thread scheduler, it has started both thread T1 and T2. Okay, so it all depends on thread scheduler whether T1 will enter this synchronized block or T2 will enter this synchronized block. Whichever will acquire the lock first will enter first. Okay, so we cannot determine that. So suppose if T1 acquires the lock first, it goes inside, and what it prints? It prints A and then this space, and after space, if it comes out, releases the lock. Then T2 goes inside, T2 acquires the lock and prints, so A space B. Now if suppose T2 first acquires the log, if T2 first acquires the logs, so it will first print B, then space, and then it will release the log. After that, if T1 acquires the log after T2, A will be printed. So there are two possibilities, A space B or B space A will be printed. So what are the correct options? AB or BA. So these are in C and D are incorrect because there is no space between A and B. Okay, so I think this is pretty clear. We cannot determine the order in which thread will be executed, right? It all depends on thread scheduler. So there can be two possible outputs of this particular program. All right, let's move on to our second problem. And this one checks if you really understand how wait works under the hood. So the question is very simple. What will happen when you run this particular code? Okay, so in Java, when you call wait on any object, the thread must own a monitor of that object, or we can say the thread must own the log of that object. So while printing this log.wait, have we acquired the log on this object, log object? No, right? So this will be an error. So you must be inside a synchronized log block where log is the object you are calling wait on. So what I mean to say is this particular log.wait should be inside. It should be inside this synchronized log block. This we have already seen in our previous lecture, right? So this is the correct thing to do, but we have not done that here. So if that is not done, what will be the output here? So it will throw an error, and that particular error will be illegal monitor state exception, right? So C is the correct answer here. So this was pretty straightforward. Okay, now this next one, question 3, is really important because it's the kind of bug that doesn't happen often, but when it does, it's super hard to debug. So here's the code. Read it carefully and tell me, is this particular code buggy or not? So if I see this wait for condition method, it waits until the condition becomes true, and signal method sets the condition and calls notify all. So seems fine, right? So what's wrong here? The issue is actually on this particular line. So in Java, you should always use wait inside a while loop and not an if statement. Why? Because of something called spurious wakeup. Now let's see what spurious wakeup means. So how is it spelled? S-P-U-R-I-O-U-S, spurious wakeups. So sometimes what happens is, suppose a thread is waiting, even when nobody has called notify or notify all, the thread may wake up anyway. Okay, so yes, even if your code is perfectly written and you have not called notify or notify all incorrectly, still your thread can wake up by itself. Now why does it happen? So this happens because of OS level synchronization and optimizations. So it happens because of OS level synchronizations and optimizations. Okay, so the JVM and the OS can sometimes wake up threads spuriously. Spuriously means falsely, as part of internal performance tweaks. This means even if this condition is still false, your thread might wake up, right, spuriously, skip this if condition, move forward and print this condition met. Okay, and this is completely incorrect. So how do we fix this? We fix this by replacing this if condition with a while loop. So if we write here, suppose while not condition, and inside this if I wait, what will happen? So in this way, even if a spurious wakeup happens, the thread will recheck this particular condition and only proceed if it's actually true. So I have also created a YouTube short on this exact topic, what I have explained to you right now. So it's a quick 1-minute visual explanation of why you should always use wait inside a while loop. So if you haven't watched that, make sure to check it out too. And always remember, wait should be used inside a while loop to guard against the spurious wakeup. Okay. Okay, now let's move to our fourth problem, and this problem is pretty straightforward. So this is the program and you have to tell what is the output. what is happening in this program? In this particular program, you have two methods, both are synchronized. So only one thread can enter the method at a particular time. Okay. So in main method, we have created an instance of this particular class, and after that we have created two threads. Let this be T1 and T2. We have called s.second here in T1 and s.first here in T2. Now we have already discussed, we cannot guarantee whether first s.second will be called or s.first will be called, right? So suppose first s.second is called. When s.second is called, this particular function, what happens? While flag wait, so value of flag is true, so this will wait, so our T1 thread will wait. After that, suppose scheduler gives chance to T2. When T2 is executed, s.first is called. Now this particular method, while not flag wait, so flag value is true, so while not, this will result in false. It will come out and it will print first. So first is printed. After first is printed, value of flag is set to false, right? And post that notify all is called. So when notify all is called, T1 was in waiting state. So T1 will wake up. T1 will wake up and check what is the value of flag. Value of flag is now false. So it will come out and it will print second, right? Pretty straightforward. So this was the case when T1 is executed first and then T2. Now suppose if T2 is executed first. So if T2 is executed first, so the value of a flag is true initially. So while not flag, so this condition will again become false. It will come out and it will print first, right? So now after that, suppose scheduler gives chance to T1. Now when T1 is executed, s.second will be invoked. Now second, what it will do? While flag wait, but here after the execution, flag is already set to false. So this particular condition will become false. It will come outside and what it will print? It will print second. So irrespective of whether T1 gets executed first or T2 gets executed first, our output will always be first, second and first and second. So what is the output? First and second, right? Okay, so what we have learned here? We have learned here is thread execution order is non-deterministic, but the execution logic is based on the synchronization and the control flags. Okay. All right, now let's look at problem number 5, and this one is not about wait or notify, but about how many threads can execute synchronized methods in parallel. Okay, so this is a simple program. In this particular program, we have created a class named methods, and in that there are 4 methods. All the 4 methods are synchronized. Okay, in our main class, what we have done is we have created an instance of this particular class methods, and also apart from that we have created 4 threads, executed method 1 in first thread, method 2 in second, method 3 in third, and method 4 in fourth thread, and post that we have started all these 4 threads, right? So what should happen? This should go independently on method 1, thread 2 will go independently on method 2, thread 3 on method 3, thread 4 on method 4, and all these can be executed in parallel, right? So how many max methods can be executed parallelly at a single point? Answer should be 4. This looks pretty straightforward, but the twist here is this is completely wrong. So the correct answer here is 1. Now why? The reason here is monitor objects. Okay, so you can see here, whenever we write synchronized on a method, a lock is acquired before the method can be executed, right? So at first glance, it may seem like the lock is on the method, but that's not true. A lock is always acquired on an object, and an object on which a lock is acquired, that particular object is known as monitor object. So every object in Java has an internal monitor, and you can think of it as a built-in lock. Okay. Now we have written synchronized here on the method itself, right? Writing synchronized on method is exactly same as what I am going to write now. So this is exactly same as writing synchronized on the method. So actually this is a shortcut where you write synchronized and method, but behind the scenes what happens here is this one. Synchronized is actually applied on this object. Okay, so what happens here is, so this is an object, and on this particular object a lock is acquired. Okay, so whenever you write synchronized this, a lock is acquired on this object. So after acquiring lock on this object, whatever this statement is inside the synchronized block, that is being executed. Okay, so this function is eventually what? So this function is eventually this. So instead of writing synchronized on method, we have written the same syntax as this. Okay, now suppose there are 4 threads which we have created, T1, T2, T3 and T4. Okay, all the threads are running parallelly. All the threads can acquire a lock. Okay, but the lock can be acquired on only one object, which is this object, right? So it is not possible that all 4 of this thread acquire lock on the same object, right? So only one thread will be successful in acquiring the lock. Okay, so if only one thread is successful in acquiring the lock, only one thread will proceed further and execute whatever is the body present inside this synchronized block. Else all the threads T2, T3 and T4 will wait outside this synchronized and wait for T1 to release this particular lock. Okay, so firstly, suppose T1 acquires this lock. So at first method 1 will be printed. After that, any one of T2, T3, T4 will be given chance to acquire the lock. So suppose T2 acquires, so method 2 will be printed. Okay, this should be method 2, method 3 and method 4. Okay, after that, after printing method 2, T2 will release this particular lock, right? Then suppose method 4 gets chance, so method 4 will be printed, and post that method 3. So all these will be printed sequentially and not at a single time. And since the lock is acquired on the same monitor object, only one thread can enter this particular method at a time, and not even this particular method. Out of all these 4 methods, only one method will execute it at a particular time, right? So how many max threads can be executed parallelly at a single point of time here? Only one thread. Why? Because the lock is being acquired on a single object, which is this object. So if I say statement, it's like in Java, this object that the thread tries to lock on is called the monitor object, right? This one, this is called the monitor object. And in case of instance method, this monitor object is this object itself. Okay, so if you are calling methods.method1, the lock is acquired on this methods instance. Okay, now let's go quickly on our IDE and see how it works. Okay, now let's come on our IDE and see. So in our IDE, we have 4 methods, method 1, method 2, method 3, method 4. We have created 4 threads, and we have executed thread 1.start, 2, 3, 4. So we have started all these threads, right? Now to simulate the execution of this particular thread, I have given here a sleep time of 5 seconds for each thread. Okay, so ideally what should happen is all are acquiring lock on a single monitor object. Okay, so at a single point of time, only one method will be executed. After that particular method will be executed, our thread will wait for 5 seconds, then another method will be executed, then again 5 seconds, then third method, then fourth method, right? So any one will be printed at any particular time. The order can be different. So let's try and run this. Yes, see, so method 1 is printed. We are waiting for 5 seconds. Now method 4 got printed. We are again waiting for 5 seconds. Now method 2 is printed. We are waiting for 5 seconds. Now method 3 will be printed. And after 5 seconds, our program will complete its execution, right? Now let's do one interesting thing. Let's create 4 monitor objects. Okay, let's create 4 classes: lock 1, lock 2, lock 3 and lock 4. Okay, instead of taking a lock on this object, let's take lock on this class object. So instead of this, lock 1 dot class, lock 2 dot class, lock 3 dot class, and lock 4 dot class, right? Now what will happen? Now monitor objects for each of the methods are different. Okay, so since the monitor objects are different, all the 4 methods can be executed parallelly. Now you will notice as soon as I run this particular program, method 1, method 2, method 3 and 4 all will be printed instantaneously, and then each one will wait for 5 seconds and our program will stop execution. Okay, so let's go ahead and print this and see. See, immediately 1, 2, 4, 3 all the methods are printed. Why? Because the monitor objects are different. Now let's do one more thing to be more clear. So lock 1 dot class. Okay, so now what we have done, we have used same monitor object for method 1 and method 2, and same monitor object for method 3 and method 4. So when I try to run this particular program at a single point of time, either one of these 2 methods will run or one of these 2 methods will run. Okay, 1 and 3 can run in parallel, but method 1 and method 2 cannot run in parallel because they have same monitor object. Now if I execute this, what could be my possible output? My possible output could be, let's write it here. My possible output could be, first method 1 will be printed, right, and immediately method 3 will be printed, right? Either method 1 or method 3 will be printed, or method 1 and method 4 will be printed, right? One from this, one from this. Either method 2 or method 3 can be printed, or method 2 and method 4 will be printed. 2 will be printed simultaneously. Now let's go and try to run this and see what happens. Yes, so method 2 and method 3 is printed, right? We wait for 5 seconds and after that method 4 and method 1 is printed. So method 2 and method 3, these two got printed parallelly because they both have different monitor objects, right? And method 4 and method 1 got executed parallelly because these two also have different monitor objects, right? So I think this is very clear to you. This is very important. Now let's go ahead and do one last thing. Okay, let's go ahead and delete all this method 3 and method 4 also, right? These two also and these two also. Okay, now public, let's make this static and used synchronized here. Now can we use synchronized on a static block? Is it possible? On a static method, can we use synchronized? So actually yes, it is possible. So whenever you use synchronized on a static method, this method, static methods are not part of any object instance, right? That are part of the class. So static method can be executed without using the instance of methods. It can be directly called using methods dot method 1, right? So whenever you write synchronized on static method, the lock is taken on the class itself. Okay, so here what will happen is, so in this case the monitor object will be this instance, right, methods, but in case of static the monitor object will be methods dot class. Okay, so if I go ahead and run this, these both can be executed parallelly because their monitor objects are different. See, method 1, method 2 both are executed parallelly. Now if I go ahead and write synchronized here also and make this static, now what will happen? Now again any one will be executed at any particular time, right? So method 1 is executed, after 5 seconds method 2 will be executed. Okay, also you can verify this. If this is static and I try to acquire a lock on methods.class. So this is completely fine, but if I try to write this here, it gives us an error. And what it does, this cannot be referenced from a static context. Reason, this static method is not a part of this object instance we have created. This static method is part of the class. Okay, so I think this is completely clear to you guys. Okay, and if this is completely clear, then I think we are clear with this also. So there are 4 synchronized block, all are present on same monitor object, hence the output here is 1. So maximum methods that can be executed parallelly at a single point of time is 1. So this concept is heavily asked in interviews because it seems like 4 threads should run in parallel, but synchronization ensures only one gets through at a time. So in all 4, if all 4 methods were running in parallel, then all of them should have printed at the same time, right? So in next video, using a problem statement, we will dive into concept of race conditions, what causes them, and how L1, L2, L3 caches play a role in this behavior. So that's all for this video. Until the next video, stay healthy, stay safe. Bye bye.